this project, we will be looking at a very useful component for your electronics projects, an ultrasonic sensor. We will be building an alarm circuit which incorporates a piezo buzzer and red and green LEDs to warn when an object has been detected or comes within a specified range of our sensor. When the object is too close, the buzzer will go off and the red LED will be lit. Once no obstacle is detected, the green LED tells us we are doing okay. Let's take a look at the objectives. By successfully completing this project, we will have mastered the following items. We will learn what an ultrasonic sensor is and how it works. This specific ultrasonic sensor we will be utilizing is a very common model, the HC-SR04, which is very inexpensive. We will learn the pinout of the HC-SR04 and how to connect it in a circuit. We will also be introduced to the pulse-in function and how it is used in conjunction with the ultrasonic sensor to perform measurements critical to the operation of our circuit. If you are ready to begin, let's get this project started. Here are the parts we will need: an Arduino Uno, a USB cable, a breadboard, 3 330 ohm resistors, an HC-SR04 ultrasonic sensor, a red LED and a green LED, a piezo buzzer, and connecting wires. Let's first address how ultrasonic sensors operate. Similar to the mechanism by which bats use to navigate, which is sonar, the sensor transmits a wave signal, which is referred to as a ping, and waits for an echo of that signal to be received. If the wave comes into contact with an obstacle, it is reflected back, and once the reflection is detected by the sensor, a calculation can be performed using the time it took for the wave to return. This is how the distance between the sensor and the object can be derived. The pulse-in function is used to measure the time between when a waveform is sent until the time it is received. It actually accomplishes this by looking at the time a signal takes to transition from low to high or high to low. We will talk more about this function when we dive into the code. If you take a look at the layout of the ultrasonic sensor, you will notice it has 4 pins. VCC is connected to 5 volts on the Arduino, and ground is connected to ground. The trigger and echo pins are connected to other digital pins on the Arduino, and the readings from these are used as part of the measurement process. Let's take a look at the circuit diagram for our project. So you'll notice here is the ultrasonic sensor, and there are 4 pins. VCC is connected to the 5 volt rail on the breadboard, and we connect the 5 volt rail to 5 volts on the Arduino. Ground is connected to the ground rail on the breadboard, and we connect that ground rail on the Arduino. The trigger pin is connected to pin 2 on the Arduino, and the echo pin is connected to pin 3 on the Arduino. For our piezo buzzer, the negative end of the piezo buzzer is connected via a 330 ohm resistor to ground, and the positive pin of our buzzer is connected to pin 11 on the Arduino. We have 2 LEDs in our circuit. For the red LED, the cathode, or the shorter pin, is connected via a 330 ohm resistor to ground, and the anode, or the longer positive pin, is connected to pin 8 on the Arduino. For our green LED, the cathode is connected via that 330 ohm resistor to ground, and the positive anode pin is connected to pin 9 on the Arduino. That's the wiring of our circuit. Okay, let's go ahead and wire up our circuit. If you look at our ultrasonic sensor, you can see that it has 4 pins: VCC, which will be connected to 5 volts on the Arduino, ground, which will be connected to ground. The trigger pin is going to be connected to pin 2 on the Arduino, and the echo pin is going to be connected to pin 3 on the Arduino. So let's go ahead and wire this up in the circuit. When you connect your ultrasonic sensor, you'll want to connect the sensor and the receiver away on the facing outside of the breadboard. That way we can test the actual obstruction. So go ahead and connect that. Let's connect the ground rail to the ground on the breadboard first. Alright, so I'll make that ground connection. And next I'll connect the 5 volt rail. So we go from 5 volts on the Arduino to the 5 volt rail. Let's wire up the ultrasonic sensor next. So first, the ground pin. We'll go to ground on the Arduino. Next we can wire up the VCC. We'll go to 5 volts. Then we have our pin, our trigger pin. That goes to pin 2 on the Arduino. Our echo pin goes to pin 3. Then we can wire up our piezo buzzer. The positive on the piezo buzzer goes to pin 11 on the Arduino. We have a 330 ohm resistor from ground, or from the negative pin of the piezo buzzer going to ground. So I'll just make sure. I'm just going to run that resistor straight to ground here. Now we'll connect our LEDs. Here's the red LED. And the green LED. The negative. Cathodes of the LEDs are connected to ground via 330 ohm resistor, so I'll connect those now. That's the first one, and this is the second one. And finally, we need to connect the positive of our LEDs. So for the red, the anode goes to pin 8 on the Arduino. And finally, for the green, the positive goes to pin 9 on the Arduino. Okay, that completes the wiring for our circuit. Okay, let's go ahead and upload the code. While that's uploading, I will open up the serial monitor. Alright, so you'll notice initially that I'm displaying the distance that an obstacle is closest to the sensor, and initially we have set the range to be 2 inches. So if an object comes within less than 2 inches of the sensor, that's when the buzzer or the alarm would go off. So right now the green LED is lit. That means our circuit is in a ready or OK status, and now I'm going to start moving my hand towards the sensor. So here we go. If you take a look at the measurements, you'll see that the distance is decreasing. So 6 inches, now my hand is at 5 inches, coming in, 4 inches, and finally, it's still good. And now, alright, you see the alarm goes off. So the red LED will be lit and the buzzer will sound as soon as my hand is with less than 2 inches from the sensor. Alright. Now I'm going to tweak the code and actually increase this to 3 inches. I'll go ahead and upload that. And now you'll see, I'm going to start moving my hand towards the sensor again. I'm within 6 inches, I'm coming closer, 5 inches. I'm within 4 inches, so as I start moving it closer, the sensor should go off. There we go. So once it's less than 3 inches, it goes off. One final tweak, I'll change the range to 5 inches. So what that means is when my hand comes within 5 inches of the sensor, it should go off. So let's start. I'm bringing it closer. I'm at 7. Here I come. Alright, so you'll see at about 5 inches, less than 5 inches, that's when the buzzer will go off. Alright, so as you can see, it's fairly accurate for longer distances, and you can play with that range setting to tweak the distance, the allowable distance of an obstacle from the ultrasonic sensor. Let's take a look at the code for our ultrasonic sensor circuit. Initially at the beginning, we define our trigger pin as 2 since it's connected to pin 2 on the Arduino, and the echo pin as pin 3 since it's connected to pin 3 on the Arduino. Next comes our LED pins, the green LED. The anode is connected to pin 9 on the Arduino, and the anode of the red LED is connected to pin 8 on the Arduino. Finally, for our buzzer, the positive pin of our buzzer is connected to pin 11 on the Arduino. The next global variable we declare is the range. This is the maximum allowable range before our alarm is triggered. The initial setting is 2 in inches, so what this means is if your obstacle comes within just less of 2 inches from the ultrasonic sensor, then the buzzer would go off and the red LED will be lit. You can tweak and change this variable accordingly to experiment with different ranges for your project. Next, in our setup function, we have to do a few things. We first set up our serial communication speed. Then we initialize the sensor pins. The trigger pin is an output, since this is the pin that generates the output pulse, and the echo pin is an input since it reads the pulse that is reflected back. Of course, our green and red LED pins are defined as outputs, And initially, we would want to send a high signal to the green LED pin to turn it on and turn off our red LED. Now we are ready to go. Let's examine the loop function. Initially, to take a reading, we have to generate a clean high pulse. So to do this, we first generate a low signal. We write low to the trigger pin. We have a short delay. Then we write high to the trigger pin, have a delay of 5 microseconds, and then we write low again to that trigger pin. So that would generate a clean, nice pulse which is sent out for us. When that pulse comes into contact with an obstacle and is reflected, it comes back. And what we need to do is measure the duration for that to occur. To accomplish this, we use the pulse-in function, passing in our echo pin in which we're taking the reading, and we want to specify that we're looking for that high to low transition. So we pass in high as the argument here. We will take a little more in-depth look at the documentation for the pulse-in function shortly. Next, we want to calculate the inches and centimeters to our obstacle. So there are a couple of convenience functions we can use. Microseconds to inches, we can call that function, passing in the duration that was taken from our pulse-in function or that was returned from our pulse-in function. And we can also determine the distance in centimeters by calling the microseconds to centimeters function, passing in the duration. Next, we simply print those values out so we can see the distances, and that was what was displayed in our serial monitor. And here's where we have the actual logic to determine if our alarm is sound. If the inches that was returned is less than the range, we know we should sound the alarm. So that's where we would turn the green LED off, turn on the red LED, and give that sound the buzzer by using our tone function. If we're okay and the inches that was returned was greater than the range, we're good to go. So the LED, the green LED would be set high, the red LED will be turned off, and there would be no alarm sounding from the buzzer. Lastly, in our program, these are the two convenience functions that do the calculations for us in microseconds to inches and microseconds to centimeters. So the calculations for these, if you require further documentation, there is a link here which explains what the calculations are, and there's some documentation from the functions here. Let's take a look at the pulse-in function, so I'm going to Google that. And here's the link. So essentially, the pulse-in function reads a pulse, either high or low, on a pin. So if you specify that the value is high, pulse-in would wait for the pin to go high, start the time, and then wait for it to go low. Hence, it's measuring the time that it takes for the reflection to come back from our obstacle. As you can see, there are a couple different variations of arguments that you can specify for the pulse-in function. The first one is the one that we used. It simply takes in a pin value and the value you want to track, whether it's high or low. You can also call the pulse-in function using a timeout additional parameter, and basically what that says is it's the number of microseconds to wait for the pulse to be completed, and if that timeout is reached, then the pulse-in function would just return 0. To summarize, in this project, you learned what an ultrasonic sensor is and how it works. You were specifically introduced to the HC-SR04 model, and the pinouts were explained, so now you will be familiar with how to connect it in a circuit. You were also introduced to the pulse-in function and the important role it plays in taking measurements for the ultrasonic sensor. This ultrasonic sensor is a very useful component and can be incorporated to beef up your robot and car projects for obstacle avoidance. You now know how to use it and interact with it using your Arduino. Let's move on to our next project.